Hello. Okay, so we hope that Zori is coming. Uh, Derek won't make it today. Uh, Jury duty, civil service, civic duty. Last homework we'll do today. Question is, do we want one more? 1 6. Here is where I thought we would be, and then I'll show you where we are. So let me move this over. All right. This was the original family, right? And we're about here. We're not going to get into any formation in this class. Just fine. You know, legally speaking, they're not going to sue me for not providing you with all of the information. We're just a little behind schedule. I wanted to have 8 homeworks. We just finished 5. Okay. There's certainly some lessons that I've learned in the presentation of this class. I think one of the major things I have a question about is the bi-weekly homework less likely to get done because you don't do it you just started in the second.
I would say so.
Yeah.
I feel like the homework quantity is not bad at all. I feel like being split up and having more like due dates, I guess, to make it more frequent enough to make sure you get it done. That's good.
Because it seems like folks would get 2 weeks to do it, and then they'd be like, oh shit, it's due this week, and then they would start it maybe 2 or 3 days before. So shorter, more frequent homeworks maybe is better than the longer deadline. So that's something I'll learn. I mean, obviously you can't change it now, but it's something I'll learn for the next time we teach it, probably in 2 years. I'm also curious about the book. When was the last time you opened the book?
So since we changed around the schedule a lot, this no longer reflects what was going on. I kind of started getting lost when we started like just touching on thermodynamics because now I'm not really sure what I should be focusing on.
Right.
But I did keep up with it for
So tying it to the material was harder.
I agree.
Yeah, so one of the things about the book is that the stuff we do in class and the stuff we do in the book, they're never intended to be one-to-one, right? Because like the type of stuff that you see in class is like, oh, here's some data that shows you what the temperature on the moon is, okay, and how it changes as a function of latitude. Whereas some of the concepts like how we do black body temperature, that is written in the book. And I would have expected you to like go into that on your own. But I think there's a disconnect between there, especially when we got off track, right? So like all of this stuff in here is stuff that we learned like 2 weeks ago. Right? And this stuff here, it's in the book, right? Chapter 4. This is here, that's chapter 4, but you know that happened here. Right, so I can see how you can get a little disconnected. So I think the things that I learned is that you have to find a way to keep the book in the forefront of your mind and use it as a resource. Lecture slides are helpful, obviously. Some of the problems I take directly from the work that we do in class. But I wonder whether or not more of a flipped classroom would help. You know, make you do the reading or the slides beforehand, then do less in class talking.
Like currently like 2 flip classes, and I feel like that helps me out a lot more to have that kind of structure.
Is that the same structure you have for computation? Because I know you have them like kind of presented themselves.
Yeah, so for computational, it's a little different because most of it's pair programming. So you do almost all, like you have like a 3-hour class time and 2.5 of it is work. You didn't take computation.
Well, yes, but I was asking more about like the book portion.
Oh, yeah.
Because I know that they read it and they like kind of present what they read and they kind of teach the whole class. Like something like that would be like just with the slides maybe. Like, that's cool.
Yeah. Yeah, I mean, we could certainly provide the slides ahead of time, provide the reading ahead of time, and just kind of do like maybe one class group problem, or like set up the problem. And then we play homeworks to keep you guys on track. Okay, so everyone has homework 5? Slightly. No one really used office hours either. That a timing issue? Incompatible with your other schedule?
Also directly after this class if possible, and that's 2 hours.
That's also right when you have your second session, and you only have like a small 30-minute session, so it's kind of hard to like.
Add them together. Okay. Okay, lessons learned. Make sure that you yell at me in the SOTIs. If you haven't done so already, I think today's the last day. Is it?
Yeah, it's really-
I'm pretty sure I could, it said that they're still open, but maybe that's wrong. Okay. Okay, then I think that no conversation about atmospheres would be complete without learning how the atmospheres behave. So that's what we'll talk about today. We use a little bit more thermodynamics, and then we'll just have like an overview of the giant planets, and we'll just kind of today and on Thursday kind of just run through them. I think it's very important to me that I get you these homeworks back. Edited so that you can update them. I think you should get 5 to me by Thursday. And then I will give you, promise is that I will meet for BC Thursday evening for a conference. So I won't be here during finals. I never planned on having anything. I don't think that makes any sense. But maybe I'll give you one more homework that's sort of cumulative. Assess how people have felt in the class. Is that fair?
Will it be like an assessment like you can have, like how you have done in your previous courses?
Well, I was wondering if it should be like a check-in, like a written check-in, or if it should just be 2 problems. The benefit of a written check-in is that you can kind of say, hey, I didn't really, this part I felt like good in, this part I didn't. The problem is that with so few homeworks, right? I really wanted to have like 8 homeworks throughout the course of the semester. We've had 5. That the content that we've covered is significantly less than normal, right? As opposed to if I give you another problem set, then even if you haven't finished all of you haven't got feedback maybe on 3 or on 4, maybe you're still working on one problem from 2, then you can be like, look, I turned that in once, but here I am doing it even better in this like final part. Right? Because there are exams that I could do for this class, just chose not to do it. Maybe that's. I'll ask on Thursday. All right. So we were talking the thermal structure of atmospheres. This is the very last part about the thermal structure of atmospheres, and it's the top. So how does that happen? Pretty straightforward. Let's see if this is a bad one. Yes, it is. All right. How does that happen? So all these layers in the atmosphere. Okay. And I'm drawing a cartoon, so that means that it's not correct. Right? There is a location where here in the atmosphere, you have things bouncing into each other. This is called the collisional. There are collisions. And when you take fluid dynamics, you choose to, you'll find out that that's necessary in order to understand a fluid. You have to have collisions in order for something to be a fluid. Because if you don't collide, then it doesn't behave like a fluid. And eventually you get to a density, remember as we go up in altitude, okay, the density is going down, right? And you eventually get to a point where the space between collisions is so large, your velocity is so high, that instead of colliding with another atom, you just miss. And you leave the atmosphere. The collisionless part of the atmosphere. The line that separates them is called the exobase. But if you talk to anyone in the industry, they hate that word. So you'll learn it, and then you'll become a grad student, and in 10 years they'll say, it's a simple word. Okay. So essentially what this means down is that you have enough energy to escape the gravitational potential energy. The rate at which the escape takes place is estimated by how light you are. And what I mean by that, let's take water. Water is what in the middle? What's the water? Make mouse, right? Okay. So what's the weight? 18, good. 18. And this one is? And this one is 1. Good. So let's imagine a nice warm soup. And let's take some hydrogen, let's take some oxygen, and let's take some water. We put them in a soup together, they are colliding. That is the nature of gas. That is the nature of a fluid. Bounce, 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 bounce. And we say that it's in thermodynamic equilibrium if all of these species are bouncing into each other such that they're sharing energy. Right? Okay. Now, if this guy bounces into this guy, and it's an elastic collision, who moves away faster? Assume he's at rest, bounces into him. This one, it's this one.
This is the second one. And steady, but this is not.
It's just not motion. This one is going to bounce and then go off, and this one is going to go off in another direction. What? Hydrogen can move a lot faster because it's smaller. So the kinetic energy, the momentum that it's imparted will be greater, because that's like if a train hit a toddler. Right? Now, if the toddler runs into the train, what happens? Yeah, it smacks, maybe just rattles himself and the train barely notices, right? This is why you don't have to buckle your seatbelt on a bus. Okay. So that's great. We understand how collisions work. Now, what happens if you have a hydrogen here and a water hits it? It's gone. You give it a lot of energy, right? And you kick it fast. Okay. And then what happens if you have a water here and you kick it with hydrogen?
Water.
Yeah, the water will slightly move, but it won't be gone. Okay. This is the basis of what we're going to talk about. Okay. So you may have heard about the Maxwell-Boltzmann velocity distribution in StatMath. Okay. Well, you should have. Fuck, they're teaching you these days. So basically what this means is that for a gas in thermodynamic equilibrium with some temperature T, remember that temperature is an emergent phenomenon. What that means is that that describes an ensemble of particles. Okay? And it says that there is some density of speeds within some delta. So you choose some speed and a small amount away from it. And you can create a distribution function. How much of the gas is at that speed? That's this question. So this says how much is at V and a little bit past. Okay. And Maxwell-Boltzmann created this thing. Okay. And it has a whole bunch of different parts. Okay. This part here is a ratio of the kinetic energy to the thermal energy. And this, let's see, mv squared, right? That's the kinetic energy. And this piece here is an exponential. Now, if you are staring at this and you love yourself some good exponentials, you immediately notice something very interesting. Okay. This is v squared. How does v squared behave? That's v.
Parabola.
Yeah, very good. That's parabola. And it goes up, right? Forever and ever and ever. So if I just had v squared, then this would say that the number of particles at a given speed would go up and up and up and up and up. Does that seem realistic? No, that seems like garbage, right? So we have our friend, the exponential, to save us. What does the exponential do?
Like create a little bit.
Okay, well, let's look at the form here, right? E to the minus v squared. Exponential decay, going down. Okay, and we've seen this before. X squared, e to the minus x squared. What does e to the minus x squared look like just by itself?
It starts on the graph and it goes on straight down.
Yeah, you know what it's called? The minus x squared is the Gaussian distribution. Okay, so it looks like this. Okay. Like that. Okay, so now we take the product of those. Right? So it's low for here, but it's high. It's maximum for both of them here. It's low for this one, but it's high. And you end up with something that looks like that. This is the Maxwell-Boltzmann distribution. What does it say? It says for a given temperature, there is some range of speeds that you'll find any particle. Some of them will actually be really hot. They'll be moving super fast. Some of them will be moving super slow, but most of them will be moving around some characteristic velocity. Okay. You see a very interesting similarity here? Like function. Boltzmann function. Okay. It's okay. Make sense? What does it look like? There we go. What this means essentially is that we can create some rest speed. This would be like a scaling number. So this is like how much of you of the normal. And then you take a ratio. So this is the normal, that's the maximum. how many of you are twice the maximum? Well, it's about 20% of the distribution. Right? And what about 1.5? Well, it's about 50%. And of course, if you want to find out the total number of particles, you do the integral under the curve, because that would tell you if you integrate the whole thing, that's all the particles. But if you want to go from 2 out, this is how many particles. So the great part of this is that V naught is the typical speed of molecules, but I have a little m in there. So even if the bath, the fluid, has multiple species in there and they're all represented by T, that emergent phenomenon, the individual particles may have different velocities. And their different velocities will depend on how large the M is. Right? So if M is really big, then 2kT divided by a big M is a small v. Otherwise, if they're small, if the mass is small, then 2kT divided by a small number is a big number. So in some mix, you'll have your slow-moving oxygens bouncing into hydrogens and making them move very fast. Right? And that is thermodynamic equilibrium. It's not necessarily saying that everyone is moving at exactly the same speed, is that their average speed is represented by something like this. Okay. Okay. We're going to call it the MB distribution because there's a lot to write. You have conservation of energy, of course. You can then rearrange this for how the masses are distributed and how the velocities are distributed. And if you just had 2 different speeds, then, or sorry, 2 different bodies, say hydrogen and oxygen, then you can find out how the energy is separated. This is equipartition. That means separated into equal parts. Equal parts. Right? And in thermodynamic equilibrium, we expect equipartition. Why is that? Because that's the definition of equilibrium. Equilibrium is using all energy for all species. Right? How it's distributed may vary. Right? Because if I give a kick to a small hydrogen, it goes faster than if I give a kick to a large oxygen. Does that make sense? And this is all just to reinforce the same idea. Okay? The heavier molecules have lower speeds. The lighter molecules have higher speeds. And therefore, the lighter molecules are more likely to escape. Okay. We've talked a little bit about the escape speed. You remember this from 2500. So V equals 2 over R. That's just one speed, right? And sure enough, you can calculate. So this would be the escape velocity, where the thing that I want to calculate is how many particles that have at least the escape velocity, or as high up as I want to go, how many of them are up there. Okay. And you can put this in for your specific distribution of particles. And I have this really beautiful, very easy to do integral, which is v cubed e to the minus b squared. Don't do it by hand. Okay. Where do you do this?
Like a
Wolfram, not a calculator. Okay. Computer. Okay. And of course, I'll let you write it like this if you want. You can do it by hand if you really feel like you want to feel strong today. And I'm just using the letter E for escape. So you can create something like U, which is a dimensionless parameter. This is a standard technique in graduate school to dimensionalize, to remove the dimensions so that it looks very similar to something that you might be able to solve for a specific quantity. And sure enough, when you do that, you can rewrite the whole equation like that. Okay, so this looks horrifying, right? If you've never done that in your life, but I promise you, people have spent a long time thinking about math, and it's doable, right? That's like not even that bad. It's horrible, but it's not that bad. You get the e to the minus e squared, that's the same thing you had before, and you just have these other pieces. You can go back in, you can find the distribution, the number of particles as a function of these things. We're gonna put the V over V naught back in. And you get a fraction of a state, okay? So what you're asking about here is the number of molecules of this species. Let's say we're looking at hydrogen. We know that the atmosphere has some scale height, it's decreasing as it goes up. How many particles are up there? And we want to know the rate at which they're lost. So this is the rate at which they're lost. The number, as a function of time, is how many escaped times the surface area. Make sense? We just calculated this. No big deal. Okay, put that in there. Do the integral, comes out with some numbers. I'll let you do that at home. And you end up with something that essentially has what's called the genes escape. So this is not a clothing company, this is a person. Genes was able to show this very early on, just using StatMech and gravity. And what they showed was that for like species, I mean, we just talked about that, the physical mechanism by which they're more likely to evolve. But also, you can turn this into a time. Okay, so what this means is that the number is going to go down exponentially. The rate that you're losing particles is an exponential, according to Jesus. And the time has fun things in here, like the temperature of the atmosphere, the mass of the particle. These will always be in competition with one another. Because if you're heavier for a given temperature, then the escape goes down. If you're lighter for a given temperature, the escape goes up. Right? So you always see these in competition with one another. Similar here, we have GMM over R. That's the gravitational potential energy holding you in. So if the mass is bigger, the time scale for escape goes down. Okay, so you're more able to hold on to your objects. And then here we have a competition. The GMM on the top is in competition with the energy from the flame. And if this is bigger, then the exponential time scale is going to be quicker, right? Than if the gravitational potential. So you have a competition in this genes version, which says, even if you have a massive planet, the thing I really care about is GMM over R. So for example, if you have the mass of Jupiter in the size of Earth, that's a very well-bound atmosphere, right? Everything is sticking very close. But Jupiter is actually quite large, right? And so the gravitational potential energy by the time you get to the edge of Jupiter might be large, right? You might be able to lose particles out there quite quickly. So let me ask you a question. And this will be a counterintuitive question. Take the Earth. Take Mars. Mars is bigger or smaller than the Earth? Small. Good. Which of the two loses more particles from the top of the atmosphere? Mars, right? That seems like the simple answer. Why is that? Little to no atmosphere, but that's not exactly what I'm hinting at. You're right, right? We know that it's lost atmosphere. But what about their sizes tells you that Mars should be losing atmosphere more rapidly, based on what we have. That's the biggest question. Is GMM over R smaller than? Is that true? Well, yeah. We have all these things that say, like, you know, you're gonna Griffith Observatory, and you stand on the scale, and it's, oh, but it only weighs 30 pounds. You're like, does that make sense? That's a measure, obviously, of force. The surface gravity is less on Mars. Okay. So that's great. That takes care of this first part. Is that the whole story? No, man. What's the temperature? What causes the temperature of the atmosphere at Mars? What is the fuel for all? Sun. Sun only fuel. Right? Like we've done a little bit of calculation about radioactive heating and whatnot. And if you go and you look at, I think it's homework 1. I asked you to compare the contribution of solar heating to the amount of heat we get from the surface. We would be frozen little ice cubes if not for the sun, right? Okay. So then you have a competition. You know Mars smaller, but the temperature is older because you're farther from the sun, right? So now it's less obvious. That makes sense how we use that? Okay, we can use some numbers here. It's big number. It doesn't fit in the calculator, but here is some comparisons between the Earth and Saturn. Okay, so we're going to look at the Earth's exosphere. That's the top. The temperature is pretty hot. Why is it so hot at the exosphere? That's exactly correct. Okay. X-rays never make it to the surface. Thank God. We'd all be fucked, right? So they get absorbed by the very first atoms and ions they encounter at the top of the atmosphere. Happens right away. And X-rays got a shit ton of energy, right? So even though the density is very small, they get a lot of energy, the temperature is high, right? This temperature is an emergent phenomenon. It behaves like this whole fluid. It's very hot, everything's bouncing, right? Because the density is small, a lot of space before they make the next bounce. Notice what happens when you go up to Saturn. Temperature is all the way down at the balmy 160. You know, that's freezing cold for us, but it's much more reasonable. Saturn, bigger or smaller surface gravity than the Earth? The M is bigger, but the R is bigger. You have Wolfram Alpha up? Or even just Google. What's the surface gravity of Saturn? And just for clarification, what's the surface gravity of Newton?
Surface gravity for Saturn is
0.5
Say that again.
1.065 grams.
1.065 grams.
That's surface gravity. I got it. So I also got it's like 44.
Now I'm confused. All right, what do we have? 10.44
meters per second.
meters per second squared. And what's the Earth, by the way?
10.8.
9.8 meters per second squared. And 10 point, we're gonna do 10 meters per second squared. Are those the same? That's a good thing I picked both of them, right? So apparently, when you stand on the surface of Saturn, which you can't do, obviously, you feel like you're standing on Earth. I mean, no one's gonna notice the 0.2. So the major thing we're looking at there is the difference in the temperature. And there is a significant difference in the temperature. Right? Earth is hotter, so therefore, who is going to have more escape? Well, hold on, let's go back and look at the velocity. Where's the velocity? This is the time that it takes to escape. Look at the velocity. The velocity is proportional to the temperature. Right? So who has the higher velocity? The Earth. So in fact, the time to escape is longer or shorter on Earth than on the Sun. All right, see if that's true. Oh, this is a much smaller number, right? This number, I don't know how to say. 10 to the 405. Yeah. So this is talking about molecular hydrogen. Okay. And molecular hydrogen here is going to leave Saturn within 10 to the 405 years. Never going to happen, right? What's Saturn made of? Hydrogen and helium. Now we see how they can be made of the lightest objects. Because, for example, here we have H2. How long is that? Imagine that's a 10. 10 to the 4. 10,000. So hydrogen is currently escaping Earth's atmosphere. What about helium? Helium is brand. Did not. It's brand new. I think there's more fun. Nitrogen? Probably chilling. We're not going to run out of nitrogen, right? That's gonna be. Nitrogen's never leaving Saturn. Not in the age of the universe. Not ever. Okay. So here's the age of the solar system, and that's the age of the right? Okay. Do we see how to interpret this information? This is what we mean by the composition of the gas giants is acid enough, it's cold enough to hold on to the lightest species. Simple? Okay. Speaking of, let's talk about these other forms. Oh, by the way, there are many more types of escape. That's all you get. If you're curious how we lose atmosphere, who do you think in the modern era between Venus, the Earth, and Mars, which planet is losing atmosphere the fastest? Venus is a guess. Venus? Venus? The Earth. Earth? Earth? You're all wrong. They are all losing it at roughly the same rate. What? That's not an option that was given. Okay, what's happening? Mars is smallest and farthest. So its atmosphere is least bounded, but Jean's escape is not the predominant form of escape. In fact, what happens is particles make it near the top of the collisional part of the atmosphere, they become ionized, and they get yanked out by the sun's magnetic field. Right? So as soon as you ionize something heavy, it feels the electrical field lines of the sun and says, hey. Okay. And similarly, Mars is small surface area. The Earth is bigger. You're like, oh, that's great. We have this wonderful magnetic field protect us. You think, oh, that's wonderful, except you have this giant surface area that the solar wind can now interact with the planet and pull atmosphere out in addition to dropping aurora. And similar with Venus, Venus is a comparable size, very close, but no magnetic field. So its loss rates are artificially high. It's a weird phenomenon that we see that happens that these three planets have about the same loss today. In the past, that clearly wasn't the case. Interestingly enough, if you think about right after the planets were formed, when all three of them likely had dynamos, which of those three planets do you think had the lowest loss? Mars, farthest away. Right? Probably true. Smallest magnetic field, smallest surface area. Good. Okay, let's talk about Jupiter. We'll try to talk a little bit about clouds. We talked a little bit about them before, but we'll just see them in action here. We'll talk about the interior as far as we understand it. And then we'll try to get to Saturn, Uranus, and Neptune. And that will probably be the end of the semester. Who's that? Yeah. Real picture? It is real. Yeah, it's from Cassini. So that's the picture. You can download it. Doesn't look as good when you get close to it on the screen, but you zoom in real life. There we go. Mass, big. Radius, big. Good. Average density. Does it float in water? No, almost, but it sinks, right? It sinks in water. Good. Moment of inertia. What does that mean? Excuse me? Very well differentiated, right? Good. Albedo. Very reflective, right? Almost half of the light gets bounced back to you. So in fact, when you look at all of the albedos, I know you haven't memorized them all. There's only one whose albedo is higher than we've seen so far. Venus. Venus is very bright because it is very reflective. Jupiter, when you see it tonight, very bright, very reflective. Good. It orbits at about 5 AU on average. Its eccentricity is very, very minimal. Takes 11 years to go around the sun, maybe 12, depending on how you want to talk about it, and about 10 hours to rotate. It has 63 moons when I wrote these in 2021. I don't know if they found any new ones, probably. And we have 2 rings that we know about. Very solid with them. Good. What's that? Big Strong. What's the name? Big Red. Not Big Red. Big Red is the name of a chewing gum. There's the word red in there. Great red spot. Great red spot. Good. Good that you can see it now. It's been observed since Galileo, and within 100 years it'll be gone. Great, right? Life would be like this. It's a storm, right? So there's no surface geology that's forcing it. It just happens that is the instability that's solved. Okay. Ooh. Ooh. Try not to get a see it. You can see it physically moving. I don't know how to make that shorter, but this is the approach of Voyager 1 from the 70s. Yeah, late 70s. We have had Pioneer 10 and 11 pass by, Voyager 1 and 2, Galileo, Cassini, Juno. Basically anything that needs to go to the outer solar system has to pass by Jupiter. I should probably put New Horizons just went by there. We are sending Europa Clipper. So Europa Clipper will take images and we'll see more. You've seen this video before? Okay, now let's hit this one. So it rotates differentially. What that means is that the outer layers rotate faster than the inner layers. Or sorry, slower than the inner. The interior is rotating faster than the exterior. Okay, this is a necessary condition for convection, that we'll show you in a little bit. Sorry, for a dynamo, we'll show you in a little bit. It also has a differential rotation with respect to the poles. So the equator rotates at about 10 hours or 9 hours and 50 minutes, but the poles are about 9 hours and 55. So even with respect to latitude, the equator is moving like that. This is sort of the idea of whether or not it even has a core. It's kind of a weird concept. So how could it not have a core? If you think about how it may have formed, most people believe that you need about a 10 to 20 Earth mass core. And then from there, you can start grabbing gas and adding it. The question is does the core survive? Is it just mixed in with all this stuff? I don't know. It's enhanced in elements heavier than hydrogen by factors of 2 to 4 relative to the sun. Okay, and what that means essentially is that when you look at the sun's composition, it matches hydrogen, but everything else, it has more of the heavier elements. Maybe that's the point. Right? You go down to temperature about 112 at 1 Earth pressure. This is not at the top of the exosphere. This is in the atmosphere. Right? So it's not the 160 we were looking at before. But it's actually kind of hotter than what we expect just from the luminosity of the sun. Why would that be? Could be the case. Could be the case. It's not currently the case. What would be another explanation? Okay, so that's an idea, right? So storms, and we thought about this when we thought about hurricanes, they are certainly functions of taking heat and distributing into the atmosphere, right? Surface heat in the form of surface water temperature into heat. It's not exactly the case here because we don't have a two fluid solution, but you are onto something here, which is interior of the planet is giving off heat. And it's giving off more heat than it receives from the sun. So on Earth, that is certainly not the case, because when you turn off the sun, the surface freezes, right? The surface temperature, due to the heat that's coming through the crust, is tiny compared to what we do. At Jupiter, it gets more energy from the layers below the atmosphere than it does from the sun. So Jupiter is shiny. Does that make sense? Yeah.
What is H?
Oh, this is deuterated hydrogen. So the D is deuterium, which is just hydrogen with an extra neutron. So this is basically H2, but it has a molecular weight of 3. Does that make sense? Okay. These are the clouds. They are cloud decks in the upper atmosphere. There's no surface. You don't see any surface all the way down. You have 2 different types of clouds. You have parallel bands of light and dark and light and dark. And what they mean is that when they are orange and brown, the so-called darker ones, they are called belts. And when they're blue and white, they're called zones. Okay, but we do know why they're that color. Why are the zones white? Yes, which one? You're so close. You are right that there is ammonia in the atmosphere, but ammonia is not white. What? It's yellow, right? So the belts are ammonia and ammonia hydrosulfide. What? What is white? Good. Is there water in Jupiter's atmosphere? These are water clouds, water ice clouds. Now, that's not so painful, right? So in fact, the same white, and we'll see this a lot through the solar system. You have white clouds, it just so happens that water ice reflects pretty uniformly. That is absolutely a coincidence. But if you have water ice, regardless of the planet that it's on, it's going to be white. That's not always the case. Ammonia ice is definitely not. It's this weird yellow brownish color. Right? And we see that also when we look at Venus. Venus is not white. It's yellow. Right? That's the sulfur hexafluoride or sulfur hydrogen. You get it, standard down. Sulfuric acid. Okay. And so infrared shows the zones, the white here is cooler than the belts. And if you remember the conversation that we had from, well, I guess you weren't necessarily into it, but the condensation temperature for water and ammonia, they're different. Okay, so it is not surprising that the zones have a different temperature than the belts and the compositions. That doesn't mean that there isn't water vapor here. Right? Just might not be condensed. Okay. So this is the same view as before. You see the flip between. I tried to line them up pretty good. So this is the true color. That's what you can see with your opals. And then this is with an infrared image. Now, what does the infrared image tell you? How hot? Exactly right. So think to yourself, you know, you're playing COD and you gotta like get them at night. And they show up because they are warm. So what's this? Good. Let's go back. Like the water's warm. So this is not always true. Water can also be good at reflecting. And maybe the water is reflecting the surface light or the sun's light more effectively. We don't want to always believe, oh, just because something is bright in the infrared. But depending on which band of the infrared you use, that will either get you the composition, that'll get you the temperature. The top zones here contain ammonia ice, NH3. This supplements at about 150 degrees Kelvin. And then, oh my God, what is it? Nitrogen, ammoniated sulfur something. Is that sulfuric acid? No.
Oh, no, it's not.
I don't think so. Below these are the ammonia vapor and then water ice clouds. So interestingly enough, right, when we look at an image like this, because we're sort of flat Earth, you know, consumers, we walk around on an Earth that is one surface, and we don't really think about stratigraphy. There is stratigraphy in the clouds. And as a function of height, you are getting different temperatures. But unlike on the Earth, where we assume that the surface is pretty much uniform in temperature, even as we just move vertically here in latitude, you might get hot, cold, hot, cold, hot, cold, right? And this might be a common altitude with very different temperatures. And so you'll have different objects condensing in or out. And right below this, you might have water ice clouds, right? And a whole band that lives underneath the ammonia clouds. Right? Whereas maybe it's too hot here. Does that make sense? That's the, that's the disk unpeeled. Of course, you know, any image like this is going to be wrong, except for that one time that. So this is basically the only guy you can ever tell. And if you decide you want to get into gas giants, it's remarkable, right? Because you may be able to look at an image like this and be like, oh, wait, these 4 markers, that must have been taken in 1997 apparition. Right? Because that's the only time the atmosphere is moving. There's no surface, right? So, you know, these things move around, they move around relative to this thing. This is something that we all sort of fix our eye on. But if you think, for an example, about Uranus, there's nothing on Uranus that you know. It's just blue, right? It's a blue dot. And Jupiter would be the same way, if not for this sort of thing that we mark on. Okay, just want to point out that the zones and belts, they are heading in opposite directions, right? Remember when we talked about Hadley circulation? That's happening here. So how many zones and belts do I get? Let's start here with dark. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, maybe 14. That could have been, I could have been arguable, you know. Maybe there's 3. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. You see all this? So you can have these little bands go past each other quite rapidly. And then they run into this. What's cool is on both sides, you can see the effect of running into this massive storm. Right, so let's say the storm's in the middle, you have fluid that's moving around either side. And as it launches off of this, it creates turbulent flow behind it. Here it creates a little circle. Like, have you seen like water in a stream and it goes around a rock and it makes little dots of it? Doing that in both directions. That's like, you see another one here? Not all storms survive. Okay, we're getting through it. We're making our way downtown. Okay, this is the infrared image of Jupiter. This is a specific wavelength band. It's really easy when you look at infrared images to get confused. Infrared is everything redder than visible, right? And you won't start off understanding what they all mean. There are different bands. These bands are either tuned to methane, they're tuned to water vapor, they can be tuned to vibrational bands in the element, or they can be broadband. They can just be telling you what the average temperature is there, right? So in this particular circumstance, this is the hottest parts of the visible atmosphere. And the infrared is moving down into those bands. Okay. So these pieces here, right? It's shiny. That means that it's hotter below the places that we can see. Now these are cloud decks. They're sitting above, likely the same amount of heat there is above it, maybe absorbing it. What's the source of heat inside of Jupiter? Is there radioactive decay? There's no core, right? Convection is a cooling factor. I need a source of heat. It is definitely a heating mechanism, but that's not this. Jupiter is still contracting. Jupiter is getting smaller through differentiation. The more material that's heavier is sinking towards the bottom. And remember one of the sources, we have three sources of heating. We have accretion, we have radioactive heating, and we have differentiation. Jupiter's still undergoing differentiation. You know, it's right? Well, it's gonna go away because there are different energetics. I don't understand it well enough to say exactly what the reason is. They tell me it's going away. I will be around to see it, so. Okay, on Earth, cyclone is a counterclockwise circulation of air in the northern hemisphere. We actually didn't talk about this in detail. We call them hurricanes. You may have heard the word cyclone before, and tornado. Cyclones and tornadoes are not interchangeable. Tornadoes are a specific local weather phenomenon. Cyclones are hurricanes just in the eastern, the western Pacific Ocean. It's a little confusing because if you think about the land, it's the east. If you think about the ocean, it's the west. I can show you what it shows. Anyway, these are the results on Jupiter of rightward Coriolis force deflection, air moving toward the center of a low pressure region. Anticyclones go in the opposite direction. That is to say that air flows away from high pressure centers and they spin the opposite of cyclones. Okay. Jupiter's atmospheric storms appear as ovals. Okay, so that. Yeah, that's not so spherical. And even if you look at all of these very carefully, they look kind of rounded. Sorry, elongated. Right? So every storm that you see here looks pulled. And we're going to find out why that is. These are all cyclones. Okay, or countercyclones, anticyclones, direction they're going, right? I think I showed you this picture hopefully before, that the great red spot, that large brown oval, is very bright in the infrared. Infrared heat is coming out through the great red spot. Right? The bright ovals in the northern hemisphere are holes in the clouds. They can see deep part of the atmosphere where it's higher. The temperature is increasing as you go down.
So just because it's just like over in atmosphere or stuff.
No, yeah, impacts basically disappear. We have watched an impact, which is the Shoemaker-Levy comet impact in '96. Smashed into the surface and saw a bunch of black dots, and they just get swallowed. It's air, right? So it's like throwing a rock in the water. Leaves no impression after some time. And so the structure that we see has everything to do with storms, with currents, and with vortices. So on Earth, we have something like, these giant currents, ocean currents, giant gyres that bring cold water, say from Alaska, down to the coast of California and make it very cold to swim. Whereas if you go to the East Coast, if you live in a place like Virginia Beach, you get warm water that's brought from Florida up along the coast, and it's really pleasant to swim, even though they're at a higher latitude, right? Those are ocean circulation currents. Similarly speaking, there are currents on Jupiter that form these storms, right? And of course, the storms form sort of regularly, they dissipate, they come back, they dissipate. Good. There's the great red spot. There's also some of these white and brown storms. White. That's the problem. That's cool, right? It looks like someone put coffee in a milk and coffee cup. Have you done it? Creates these little like ripples. all that structure is. Oh, the white ovals, sorry, white ovals have a lower. They tend to be above the cloud deck. The brown ones are not, they're lower. Oh. Here's a special case. Here's our friend, very red spot. It is okay, massive. So I want you to have a look at these numbers really quickly. Okay, that's 40,000 kilometers. For context, how wide, what is the diameter of the Earth? 13,000 kilometers. Good. So it's about that wide. That's the whole of the Earth. Okay, and much bigger, obviously, this one. It has a 6-day rotation period, so the whole thing rotates in about 6 days. Go around, so you drop a little parachute here, take you 6 days, then all the way around. It's anticyclonic, so that means that it starts in. It's been around for at least 300 years. How do we know that? Galileo was the first one to see it. Oh, bro, there's this thing, right? Okay. And interestingly enough, most of the great red spot is high altitude clouds. So when we were talking about earlier, the brown spots kind of see lower. That's just not the case here. Right? It sees like they can do basically. It's not exactly altimetry because we're not bouncing lasers off of it, but when we do observations, we can find out how far down the object is. Right, so they find out this is pretty high up. Okay. Most of the spot is about 10 degrees Kelvin cooler than the white clouds that surround it. This is counterintuitive. You have to remember that it's physically higher, 8 kilometers higher than the white clouds. So this is quite hot, bringing up heat from below, but it's physically taller than the white clouds. Okay. Okay, here's another. Oh, this one isn't so bad. Pretty set, right? You can see this behavior this way. And you can see how the bands and the zones are moving in opposite direction. And especially at the interfaces, you know, devastating fluids, this won't mean anything to you, but when you have two fluids shear past one another, they mix at the boundary line, if they're allowed to. And what they'll end up doing is what you see exactly here. They'll start spinning up, right? As one moves past the other, they start forming little ends. They form little turbulence, depending on whether or not it's fast or slow motion past one another. So you can see down here, it's less intense than it is up here in the wake of this large. Okay. We've been to Jupiter. We've dropped the thing. Whee! That's how we know what the composition of the atmosphere is. Down, down. He dropped the probe, parachuted in with a heat shield. It stopped transmitting at about 24 times the Earth's atmospheric pressure. Which you think to yourself, that's not very good. How far is that in water? I know. Yeah. That's how. I think a fathom is longer than a mile, right? Maybe I'm thinking of furlong.
Yeah, I think the fathom is just the difference in temperature, which is like 10, or a difference in pressure, which is 2.
Okay. Yeah, so it's about 240 feet if you're in the water. But you're not. you're in the density of Jupiter, right? And so of course that is quite a big difference. And it's many thousands of degrees. Well, I don't know if it's thousands. I think it got up to it. Remember the thing you remember here is that it's pressure and temperature going up as you fall. So they found that wind speeds are higher below the cloud deck. But one thing to keep in mind composition of Jupiter's atmosphere. It's really fun. Okay. So starts up here, very high, right? And then it gets cold, and then it gets hot again. Okay. And this is temperature. This is altitude up. And at some point, you get to the location where water ice can condense. And you have the ammonia ice. And the oops, 3, right? And below that, it's too hot to condense. So you don't have clouds. So I want you to imagine what it would look like as a human being if you were able to be below the cloud. Just gas, but you can't see any clouds in it. So you look up, you can see the clouds as they're falling, and below you, just nothing in darkness. And then you look out to the sides, right? And it's kind of a little bit like the Venus images we showed, but way in the back, where it's just yellow in all directions. Very similar, but now of a more orange reddish color. And it'd be like underwater, but you can't see the water. So they also showed that there's an energy source for winds. That there are certain chemical processes that go on below the cloud deck that are powered by the winds as opposed to simply the air. So we have something called photochemical models on Earth, which means that light hits the atmosphere and produces new species. So the production of ozone from the absorption of ultraviolet and vice versa. Sorry, the absorption of ultraviolet from ozone, vice versa. But here, the very fact that the wind is moving can power chemical reactions. And there was no hint of low-lying clouds of H2O. And as it fell, as the probe fell, the hydrogen to helium abundance ratio was still the same, which means that the atmosphere is well mixed. It's not like hydrogen sitting on top of helium, right? They're all mixed up together. So that fraction is the same all the way through until it died. Okay. Jupiter's interior, okay, this is pretty funny. It decreases faster than linear in the radius. We calculated the linear decrease, I think, at the very beginning of the class. So this is even more convenient. If there is a mass of the core, it's about 4% of the planet, but it's compressed. So if there's a core there, it's 11 times the mass of the Earth, but less than the size of it. There's very high pressures. So the pressure at the core would be something like 8 times 10 to the 7 Earth atmospheres, something like 25,000 degrees Kelvin, and something like 20 grams per cubic centimeter. Is this hot enough to ignite hydrogen into helium? No. Do you know that number off the top of your head? Okay. It's about 15 million degrees Celsius. So interestingly enough, it is hot enough to see. The interior of Jupiter is shiny, just thermally invisible. So fucked up or what? We're going to continue. The compression changes hydrogen into a liquid metallic state. Let's remember what the word metal here means. The metal does not mean that it's a solid. It means that it's sharing its electrons freely. Metallic is a state of friendship, not a state of matter. Right? Okay. And the liquid material either surrounds or comprises the core as a whole. Jupiter emits about twice as much power as it receives from the sun. Okay, any questions about this? Pretty cool, right? Kind of weird. So Juno is trying to understand a lot of these questions. What is the distribution of matter in the interior? How did you perform? Did it have a core? And it does that by looking at those compositions that I kind of just brushed over. It's understanding the relationship between Jupiter's composition and the sun's composition tells us whether or not they're made of the same material, whether one of them is modified, whether they had a core, and so on. We'll have more answers to that in the next few minutes. Questions, comments, concerns?
Does the atmosphere slow down Jupiter a bit?
Other way around, actually. The Jupiter's atmosphere, its rotation comes from the fact that it is contracting, right? It's speeding up as it contracts. And in general, because it's emitting more heat than it's receiving, it has an internal source of heat with which to power its winds. Right? It's sort of counterintuitive, but I think it's a very interesting system.